in the second exercise, you're asked to call a function func with a lot of parameters and with a return value. Now, look at those types here. We have long longs, we have a pointer to a long long, we have a long long as a return value, we have some ints. If you want to do a function call, you first need to know these types, how big are they, and how am I going to pass this. So we have compiled this function func with GCC. That means the only way to correctly call this function is by following caller conventions from GCC or from any compiler. What are the conventions that GCC will follow? Well, the RISC-V calling conventions. So you can only call this function. You can either try to reverse engineer what is happening here. This is unoptimized GCC code, by the way. You can instruct GCC to write this function a lot shorter, but we explicitly did not do this because it's not the point that you understand this function. You need to understand that you can call this function simply by knowing the signature of the function and knowing the calling conventions. And that's the goal here. Call the function without actually understanding the function. And we can check the result, because the result is simply the sum of the arguments. The last one is an address, so we dereference that one. So the result here should be 21 of this full execution, which is 6 plus 5 plus 4 plus 3 plus 2 plus 1. And we've passed the address 6. The address of this long long, we passed the address here. Keep that in mind. So the writing the main function should be relatively straightforward. And if we were on a, if let's say all of these arguments would be int, then we would be quickly done. I bet a lot of you tried to load first parameter A0, we load 1 into A0, 2 in A1, 3 in A2, and so forth. And then the address of I in A6 or in A5. Well, that's incorrect. Why is this incorrect? Well, we have these data types here, long long C. Let's go to the calling convention. What do we see? Well, a long long, that's 8 bytes in RISC-V 32 bits. Now in RISC-V 32 bits, our registers are 4 bytes in size. That means you cannot pass a long long using one register. It's simply not possible. You have to use 2 registers to pass a single long long. So in this document, I'm going to just say it, in this document is described that if you have a value that fits into 2 registers, you can pass this value using both registers. If it's bigger than that, you have to pass it by reference. You have to pass the address. In this case, it's not bigger. No, it's simply a long long. So we can fit it into 2 registers. Now the main question is going to be, how are we going to fit it into 2 registers? And this has to do with the bit representation of our program, of our values. So let me open a notepad here. And let's say we have a binary number, and this binary number consists of ones, 32 times, 32 of these ones, and then 32 zeros. So we can all agree this would be a 64-bit number. Each bit either has a 1 or a 0. Now, we have 32-bit registers. Let's say A0 and A1. They can hold 32 bits. So if you would use both registers to pass a 64-bit number, so this is a 64-bit number, let's say we want to pass this into 2 registers, we could simply split right in the middle. And that's exactly what we're going to do. Now, here's the convention. In A0, we will put the low order bits, and in A1, the high order bits. What does it mean? Low order bits, that means the rightmost bits. So this is the lowest bits of your, let's say if you would address each bit individually, the lowest address would be the rightmost bit, and the highest would be the leftmost. So the right part are the low order bits, and we pass them in the first register. And then in the second register, we pass the high order bits. So how do you pass a 64-bit number? You split it into two in the middle, so that you have two 30-bit binary numbers. You pass the high order 32 bits in the second register and the low order in the first one. Now, let's think a little bit more about what that will mean if we pass, for example, the value 5. Long A equals 5. 5 in binary is 101. 5 in binary in a long would be a bunch of zeros, 101, and in total this would be 64-bit long. Because you have a long, you reserve 64 bits, 8 bytes, and you just place the value of 101 at the very end. So if we split this into two 32-bit numbers, so this is a bunch of zeros, in total 64. If you would split that, let's say right there, well then your left part, the high order, would be 0, and the low order, the value there is, well, a bunch of zeros, 101, in binary, which is in decimals the value 5 again. You're just cutting off a bunch of 0 from the start. So if we want to pass this into two registers, well, then you would say A0 would be the value 5, or the value binary 101, right? The value is like, it's the same as 101 in binary. And A1 would be 0, because the high order bits are just 0. So to pass the value 5, if it's a long, you pass it into two registers. The low order bits you put into A0, which are simply the value 5, and in A1 you put the value 0. And now we are ready with this information to take a look at the actual solution of this exercise. Let me open up the assignment again. There we go. So we have these arguments. How are we going to pass these arguments? Well, let me put it up here. The value 1 of A, so it's 1 here, we're going to call the function, right? First argument is an int. So we pass the value 1 as an integer. 4 bytes in size, fits in one register. The register we choose is A0, the first register available. Next, we pass the value 2 as a long. Let's see what a long is in size. Oh, a long on risk 5, 32 bits, is 4 bytes in size. So, again, fits into a single register. We will pass this in A1. Next, the value 3 is a long. So we have to pass it into two registers. And just like in the case with the value 5, only the low order bits will have something of significance, and the higher order bits will be just zeros. So what we do is, this was A0, this was A1, so C will be passed in A2 and A3. C is A3 and A2. The high order bits in A3, the low order bits in A2. So we pass the value 3 in A2, which is the low order bits, and the value 0 in A3. I'm not going to do this again, because we do exactly the same for D and E. Exactly the same. Low order bits, high order bits. This is all longs. And now we reach the end of our A registers. We have 8 A registers. A7 is the last one. And now we need to pass another argument. How big is the argument? It's not 8 bytes, pay attention. This is a pointer, which means this is an address, which means it's just 4 bytes in size on a 32-bit machine. Because it's a pointer, it's an address. So we would pass this normally in A8, but A8 does not exist. Once you run out of registers, you have to pass on the arguments using the stack. So our very last argument has to be pushed to the stack before we call the function. So when we call the last argument, which is the address of I, that's what we need to pass. So we load the address of I into T0, right here. T0 has the address of I, and we then have to push that value to the stack before we call the function. Again, this is calling convention. We push the address of I to the stack using incrementing the stack point or decrementing it by 4, meaning reserving 4 bytes of space on the stack. And then we write to the current stack pointer, so in this newly reserved space, we now write the address of I. So we have pushed the address of I to the stack, and then we are ready. Registers are done. We've put the value of I on the stack. We can call the function. Now, last thing here, the result of this function is a long. That means the high order bits will be passed into A1 and the low order bits in A0. So if you want to store this result in memory, you need to make sure that you store the low order and the high order bits both in memory as well. So you could say, we load the address of our result symbol here. We load the address first into T0, and then we store at this address, we store first the low order bits, and then the high order bits go at the higher address. So this would then store the result at the memory address result. And then at the end, we still restore the stack pointer here. We pop our value again. So let's execute, assemble, and let's run this program, and we will see if everything's correct. We get here the value 15, but this is a hexadecimal value. This is the result fields in memory. Now if I write this as a decimal value, then you can see here it's 21. This is 1 plus 2 plus 3 plus 4 plus 5 plus 6. If you don't have 21 here, you have passed your arguments incorrectly. So this shows us we can call a function, this function, compiled by GCC, and we can immediately call it very simple. And that's why we use calling conventions. Anyone can write a function, and you can just call it without having to know the implementation of the function. That was it for exercise 2.